pumping from saturated liquid at state 5 to a compressed liquid at state 6. And we know if we're doing an open system balance over the pump, we get this equation. But we also know from our steady flow reversible work equation, and everything's reversible in this cycle, at least that's how we analyze it. We know that that steady flow work is equal to this integral, steady flow work. And we also know that because we have a liquid between states 5 and 6, we can pull out the volume because it's essentially incompressible. So we can calculate H6 minus H5 as V, the specific volume, times P6 minus P5. So one of the things that always trips people up on analyzing this cycle is they try to find these in the tables. And it's easy to find H5 because it is a, what state is state 5? Saturated liquid. What people struggle to find is H6. And you don't even want to try to look it up in the tables. Instead, what we want to do is calculate the pump work using this equation. And then if you need H6, which we do, we work backwards to get it. Because we know H5 is the saturated liquid state. And to get the properties of V here, we just use the saturated liquid state. So that's at 5. And if we want the actual pump to work, we have to use the compressor or pump efficiency. And if we want to analyze this cycle in detail, basically you have to find all the enthalpies. So we need 4 enthalpies. 1, 3, 4, and 5. In our case, at least in the homework, we're going to assume that the turbine and the pump are both reversible, so you won't need to work with this state 4 here. Notice that 4 prime, going from 3 to 4 prime is a vertical line corresponding to no change in entropy. And the actual turbine going from 3 to 4 shows an increase in entropy, but the exit is still on this constant pressure line, P4 equal P5. Okay, so let's, I guess another thing we should talk about. This is our definition of thermal efficiency. So it's the net work out. This is a positive number over the heat in. And if we do an energy balance, steady state, for a closed system balance over the heat engine, we can rewrite it in this form. Do you want me to write down that energy balance? We better do it. So let's go back over here. We know that we use our energy balance over the heat engine. Write that just as well with or without the dots. It doesn't matter. So we use that. We solved that for the workout over here and substituted it in here. And that's how we got the second form here. And then each of these Q's, we can do an energy balance over the condenser. The condenser is going from 4 to 5, and then over the boiler, which is going from 6 to 3. So 6 to 3 is the boiler. Constant heat addition in the boiler. Those are all labeled up there. So any questions about what's going on? Yes.
So for the pump, that is the efficiency of the holes, right? Like, I guess, can you explain the difference between the N beta and NC?
So what's the difference between N beta and C? Theta here stands for thermal. It's the Greek letter corresponding to our letter T. T for thermal. And the C here stands for compression, which corresponds to what we're doing in the pump. So those two definitions they're both written, no, this one is written as what we want divided by what we have to put in to get it. This one is based on the concept of isentropic efficiency, where this is the best we can do, and we know that the actual work is going to be greater than that, so we divide by something that's between 0 and 1 to make it bigger. And with the turbine, this would be just the opposite. Does that answer your question? Okay. So let's do an example. Any other doubts or questions? Okay, so here we have a great big power plant, 1,000 megawatts. That's a big power plant. And we don't know what's supplying the heat. We just know that it's using steam as the working fluid. And we're going to analyze the simple ideal Rankine cycle. And when we say ideal, we mean there are no irreversibilities. So the turbine is perfect, the pump is perfect, and we want to calculate all these things. Here are our key assumptions. We're even going to take the generator to be perfect. So the turbine is going to put out 1,000 megawatts, and 100% of that's going to be converted to electricity. Okay, and the things we know here that we need to solve the problem. We know the power output. We know these two properties coming into the turbine. And we know this property coming out of the turbine. Okay, so that's all we know. How do we do this? So in solving these problems, the very first thing I like to do is sketch it on a TS diagram, because it just organizes all of your thoughts. And we're going to start at state 3, coming into the turbine, because we have complete information at 3. And we know there the pressure P3 was 10 megapascals. And we also know that T3 is 500. Just to remind you, whenever we use the tables, we have to use the tables here. This is high pressure steam. We don't even want to think about using the ideal gas law. And CCP, partly because we have a lot of phase changes going around the cycle. So we have to use the steam tables. And in order to use the tables, we always need 2 independent intensive properties. We've got those at 3. It is the only place on the cycle where we have complete information, although that's also true at 5. We have complete information there because we know it's a saturated liquid, and we know the pressure is 10 kilopascals or 0.01 megapascal. Okay, so which table do we start with? We need the properties at 3. We could just work on faith and start with which table? We could could start with a superheat table, and that's good if you're experienced, but if you recognize, for example, that 500 C is greater than the critical temperature of steam or water, you could just go directly to the superheat table, but if you're not sure, you always go to the saturation tables. And you'll find that, yes, indeed, we're superheated. So we go to the superheat table at P3, 10 megapascals, and we look up H3. H3 is equal to 3375 kilojoules per kilogram. And we also look up S3. And that is equal to 6.5995. And the units there are kilojoules per kilogram Kelvin. Okay. So the next thing we do is recognize that state 4 prime has what entropy? What is the entropy at 4 prime? It's S3. So S3 is equal to S4 prime. That's 6.5995. And now, we also remember that P4 here, which is equal to P4 prime, is equal to 0.01 megapascals, which is equal to whoops, come on. 10 kilopascals. Okay, so how do I get the properties of 4 prime? We have entropy and pressure, we need enthalpy because we want to know how much power is coming out of the turbine. So how do I get H4 prime? So we may have to interpolate, but before we even think about interpolation, what's the method we're going to use? How do we determine which state we're at for prime? The way it's drawn up there, it's drawn as a saturated mixture, but we don't know that. That's just a cartoon. We could be superheated at state 4 prime. So how do we figure out what state we're in?
Is this where we integrate?
Pardon?
Is this where we would want to integrate, like look up a specific volume and?
No, that's, you're thinking of the, that's 5 to 6. That's the pump. For the turbine, we don't use that approach because V is not a constant. It can be a mess. So instead, we're just going to look up H4 prime. Which table do we go to? We go to the saturation table, and we'll go to the pressure table because we know it's 10 kilopascals, and we'll look for S. Yes?
Was the pressure given a problem, or how did you know
P4 was given.
Okay.
So you have to be given P4, P3, T3, and the power output. Or some other, maybe one of the heat inputs. You have to have enough information to solve it. So we have enough there. So we go to PSAT is equal to 10 kPa. And we look up